Welcome to the lecture on catalytic organometallics. This is part 26, and subject of today are lanthanoids in catalysis. Well, lanthanoid salts are often used as Lewis acids. And what is so special about those lanthanoid salts? That we will discuss today. First of all, these lanthanoid salts have generally a very low toxicity. A low toxicity comparable to sodium chloride. So, and lanthanoids, well, seem to be seldom. They are called rare earth metals, but they are everything else but rare. In fact, for instance, cerium is more abundant on Earth than zinc or cobalt. And even thulium, a word which, or an expression or name you very seldom hear of, this is the most seldom lanthanoid. Well, it is more abundant than silver or a non-metal, of course, iodine on Earth. So the problem with thulium is you find it in low concentration and it is difficult to purify it. For instance, thulium oxide is obtained pure by fractionating crystallization 15,000 times. Okay, this makes it expensive, of course. Yeah? So the cheaper lanthanoids cost about a few euros per gram. So for lanthanoid salts, the oxidation state +3 +3 is preferred. And all applications as Lewis acids in catalysis are indeed salts with this oxidation state. However, we have already discussed lanthanoids in the oxidation state +2. I hope you remember that was the preceding semester, samarium chemistry. So, samarium iodide is an 1 electron reducing agent, produces ketyl radicals. Well, this is Gary Molander's chemistry, mainly developed by Gary Molander at Boulder, Colorado. So let's add the name Molander here. On the other hand, +4 as an oxidation state also occurs. For instance, cerium in the oxidation state +4 as cerammonium nitrate. You certainly remember CAN oxidation. Simple example, naphthalene or naphthalene derivatives are oxidized to the corresponding naphthoquinones with 6 equivalents of CAN at room temperature. Well, acetonitrile water mixture, 6 hours reaction time, and 95% yield. Well, these lanthanoid salts in the oxidation state +4 are stronger oxidizing agents, for instance, than chlorine, elemental chlorine. And that means they are really strong oxidizing agents. So, in stoichiometric organometallics, we discussed one example, a name reaction, where lanthanoid +3 salts were applied. Cerium chloride. That was the so-called Lewis reduction. If you have an alpha, beta, and saturated ketone, you can reduce that with sodium borohydride in the presence of cerium chloride. Then reduction selectively takes place as a 1,2 addition process, not as a conjugated addition process. To get this high selectivity, certainly far above 90%, you need cerium chloride. So, further general remarks. Let us compare it to iron 3. For iron in the oxidation state +3, we have an ionic radius of about 70 picometers. Lanthanoids in the oxidation state 3+ are much larger, about 100 to 130 picometers, depending on the coordination number. It starts at a coordination number of 6, but it can be even a coordination number of 12. Although those lanthanoid salts in the oxidation state 3+ are rather large, they are nevertheless considered as hard Lewis acids. Remember, the larger something is, then it is more regarded as soft. In this case, we stay with the classification hard Lewis acid simply because it is in the oxidation state 3+. Okay? So, these hard Lewis acids have a strong oxophilicity. Since they are rather large, they allow even bulky coordination ligands, but these are bound by rather labile ionic forces. And that means they are easily bound and easily go off again. Fast reactions, fast ligand exchange, and this is one reason why these Lewis acids are very nice catalysts. Binding and dissociation works rapidly. That means high turnover rates. Very often excellent yields with catalyst loading of a few mole %. Another thing that is very important, well, Usual strong Lewis acids, which are generally normally used, are iron 3 chloride, aluminum chloride, BF3 etherate. Working with these Lewis acids mean you have to exclude water. You have to work under dry conditions. And this is the main difference. With those lanthanoid salts, you can work in aqueous solution or in the presence of water, and they don't hydrolyze. Actually, you can recover these salts again from the water layer. We will see a few examples of that. First example, a Michael type addition reaction at methyl vinyl ketone in acetonitrile at reflux temperature This would be the Michael adduct. First catalyst system, cerium chloride as heptahydrate, stoichiometrically, reaction time 4 days, and yield 30%, certainly not a reaction to be very happy about. If one adds a bit of sodium iodide, so, well, cerium chloride as heptahydrate, but just 0.2 equivalents. That means 20% catalyst loading, plus 0.1 equivalent of sodium iodide, then 12 hours reaction time are sufficient, and a 96% yield was obtained. So the actual catalytic active species is not known. One can speculate that well, one chloride is exchanged against one iodide, but it certainly makes a difference, which we can further explore with the next example. Well, with reaction conditions, not the same reaction conditions because it's a short reaction time. So, cerium chloride, hydrate, again, acetonitrile reflux temperature, 1 hour. And, well, allylic alcohol as reaction partner. Then, well, the Lewis acid will attack at this acetate group, leading to an elimination reaction, and the stabilized cation then is trapped by the allylic alcohol, giving this product. We get a different selectivity if we add a bit of sodium iodide. Then this functionality remains intact. Finally, this position is protonated and the stabilized carbocation is trapped. Well, similar to simple THP ethers. You know, these protecting groups. This moiety is introduced as a protecting group for alcohols. This is essentially the same. Oh, sorry. Oh, no. Yes, this here, you have stereoisomers. In that case, you have preferentially this isomer so next example. A type of Mukayama aldol addition reactions. So invented by Shu Kobayashi in the early 90s. He introduced lanthanoid triflates as very active Lewis acids which can be used in aqueous solution. So, a nice example. This TMS enol ether reacts with aqueous formaldehyde. Again, you can't use titanium tetrachloride in this case, of course. Reaction is done in a water THF mixture, the ratio 1:4, room temperature, and ytterbium triflate. With 10% catalyst loading is applied. Again, you can recover the catalyst almost 100% from the aqueous layer, besides obtaining a very nice 94% yield of that product. Actually, the water is essential for obtaining a good yield. Well, 50 equivalents of water to the lanthanoid triflate turned out to be the optimum. That has been tested by the Kobayashi group. So using water as the solvent might cause another problem, because some of the reagents are not very good soluble in water. So therefore, the next example, the same TMS enol ether benzaldehyde as the substrate. In this case, water as the solvent, again, room temperature. Scandium triflate. Again, 10% as catalyst. And now you simply need a surfactant as a reagent which helps to get more lipophilic substrates into solution. SDS is a surfactant which has been frequently used, and this is sodium dodecyl sulfate. So the structure is this. %20 SDS is added, and the product, well, should be clear for everyone. Mixture of diastereoisomers, 88% yield after just 4 hours reaction time. Same reaction conditions. So again, scandium triflate, 10%. SDS 20%, room temperature, water as the solvent. Now, a small but important change in the substrate of the TMS enol ether. %84 yield. So what is so special about this reaction? Well, in this case, it's the TMS ether of an ester enolate. And as you know, those are especially sensitive for hydrolysis. Nevertheless, under these reaction conditions with that sodium dodecyl sulfate, it works very well and gives a nice yield. Almost same reaction conditions as before, except that the scandium triflate was applied in just 5%. A Mannich type reaction has been tried. Benzaldehyde as the aldehyde component. You need an amine. In that case, an aniline, orthomethoxyaniline, forming the iminium cation. And now, for the Mannich reaction to proceed, you need an appropriate nucleophile. That was, again, a TMS enol ether. Resulting in this beta amino ketone, 87% yield were obtained. Another interesting reaction. We have an ester and in this case a primary amine. Forming a carboxylic acid amide and ethanol. So looks like easygoing reaction. Actually, it isn't. Certainly it's exothermic, yes, but it is, under moderate reaction conditions, a rather slow reaction. And please keep in mind, if you add a Lewis acid or a Bronsted acid for catalyzing this reaction, you would like to activate selectively the carbonyl group by protonating the carbonyl group. Unfortunately, that amine is far more basic. And Bronsted acids and certainly, generally, also Lewis acids prefer to coordinate to the amine. Well, okay. Let's have an example or two. Chloroacetic acid ethyl ester plus benzylamine, ratio 1.2 to 1. Without solvent, 12 hours at room temperature. Then you get a mixture of 3 products. This secondary amine, the product of, well, the SN2 reaction, 11%. Then a bit more, 13%. Of the corresponding tertiary amine, and just 9% of that amide. Well, you will get some, these were identified and isolated. You will also have, of course, products in there. They're then a second equivalent of the benzylic amine reacted in a nucleophilic substitution here, of course. So, but same reaction conditions, but adding just 2% lanthanum triflate then a 90% yield of this target product was obtained, and this is very modern chemistry published in Organic Letters this year on page 2018. So let's change to accomplishments of lanthanoid catalysis in enantioselective synthesis. Here we have an interesting structure. Sorry. An europium-3 salt made from a camphor derivative. So this is chiral, of course. And well, it's you can buy that. You don't have to synthesize that. It's available already maybe 30 years or more. Why? Because this is a reagent for NMR spectroscopy. A lanthanoid shift reagent. So, if you have a suitable product, well, as a mixture of enantiomers, well, then you, of course, by NMR spectroscopy without an additional reagent, you can't determine the ratio of the enantiomers. But add that europium salt, it becomes possible. So, you can try that as a chiral Lewis acid, and it works. Unfortunately, not to complete satisfaction. But in principle, it works. This case, yeah, well, you can call that a heterodiels-Alder reaction. This is the intermediary hetero-Diels-Alder product. However, it's not isolated under the reaction conditions. An additional elimination takes place. Well, this one is eliminated. And you get a conjugated alpha beta unsaturated ketone conjugated to that oxygen here. (58% enantiomeric excess). Well, as I said, the threshold nowadays is at about 90% to be considered as useful. Well, one has to optimize the ligands for achieving a higher enantioselectivity. The next example, a very high enantioselectivity, was reported. It is a rather recent example by Shibazaki. In chemistry, a European journal, 2011, on page 1915. So, the catalyst, well, is something evolving from a dynamic equilibrium where lanthanum nitrate as hexahydrate is involved. Then a chiral amide with lots of coordination sites for the lanthanum in the oxidation state 3+. Actually, it's a derivative of the amino acid valine. And valine tertiary butyl ester is another component of this dynamic mixture. Applied in the ratio 1 to 1 to 3. So, and what has been achieved with this applied as 3% catalyst. So, this mixture means it's applied as 3% catalyst for this transformation. So, here we have a special acidic position. Enolates can be formed under the influence of our Lewis acid. Reaction partner is this azo dicarboxylic acid ester. Well, first of all, again, that 3% catalyst, 0 degrees, 24 hours in acetic acid ester as the solvent. Secondly, hydrogenation with a rhodium catalyst. So, what happens? Enolate is formed, reacts with this functionality. This is the nucleophile, this is the electrophile. We are forming essentially a carbon-nitrogen bond. Hydrolysis and especially that hydrogenation destroys the nitrogen bond which remains there, and well, in end effect we have then introduced an amino group enantioselectively. Better 90% yield and 95% enantiomeric excess. Another example, a 1,3-dipolar cycloaddition. Well, one development from, again, Kobayashi's group. Here is the olefinic component for the 1,3-dipolar cycloaddition reaction. And as the 1,3-dipole in this case, a nitrone was chosen. So, the nucleophilic oxygen will form a bond to this position, whereas this electrophilic carbon will form a CC bond to that position. So let's see. This should be correct, hopefully. So, what about the stereoselectivity? This one is the one that has been reported. 92% yield, 96% enantiomeric excess, and this product has been used for further transformations, of course. After a few steps, they then reached their target, a beta lactame, which is, as you know, interesting in the field of antibiotics. This one. Last chiral lanthanoid catalyst for today is one remarkable development from, again, the Shibazaki group. Actually, it is a bimetallic catalyst. With lanthanoid in the oxidation state 3+ as the Lewis acidic center, and present in the same molecule is a basic alcoholate with lithium counter anion. Really an interesting structure. So, let's put that lanthanum 3+ in the center. Add six oxygens around it. And all those oxygens belong to those binole units. So we need 3 lithium countercations that the whole molecule is neutral in charge. This is the structure. And this structure and similar other examples with atrope chiral phenols have been used for various purposes. For instance, this one in a so-called nitroaldol addition. An aryl group, aldehyde functionality, plus nitromethane, about 10 to 50 equivalents. THF, well, 50 equivalents, then you can say THF is a co-solvent. Minus 50 degrees, 3% catalyst. %90 yield of the beta hydroxy nitro alkane, 94% EE, and those beta hydroxy nitro compounds are of course interesting. By reduction of the nitro group to the amino group, you get chiral amino alcohols. Somewhat more of the same catalyst, about 20%, were used for the enantioselective aldol addition process. Again, 50 equivalent of that pre-nucleophile. THF minus 20 degrees. Slow reaction, 185 hours. 71% yield, 94% enantiomeric excess. Well, excellent enantiomeric excess. Moderate yield, slow reaction. As I said, 20% of that catalyst, rather high catalyst loading. So, highly interesting chemistry, highly interesting reaction, usefulness, well, one might discuss about that. So, what are the alternatives? Well, and there are, of course, alternatives. Unfortunately, from organocatalysis without metals, so not within the scope of our lecture. So just proline, you know that amino acid as the catalyst. And at least for this case, in a rather short reaction time, 97% yield of this product and 96% EE. If I remember it correctly, this is a result from Benjamin List at the neighboring Max-Planck-Institut for Kohlenforschung. Well, however, one very last reaction, also in this context. Let me see, here we have some place left. A similar aldol addition process has been optimized. This benzaldehyde paranitro cyclohexanone as the other substrate. Two stereogenic centers have been formed. Diastereoselectivity, anti to syn was 16:1. High diastereoselectivity, quantitative yield, and better 99% EE. So, what was important for achieving this optimized result? 20% proline, DMSO, and a co-catalyst. Now a metal Lewis acid co-catalyst, zinc chloride, 10%. Well, and this is the message. Maybe you can achieve the optimum if you combine organocatalysis with transition metal catalysis. Maybe even combining speculative proline with lanthanoid salts. Of course, not necessary in this case. You can't improve that result. So, thank you for listening. Next week, Tuesday, we will discuss iron catalysis, and maybe already also copper catalysis. Thanks for listening. See you next week.